This is Bob McFetrich with Beckwith Electric, and I'd like to thank you for downloading Session 4 of our IVVC program. In Session 4, we will be discussing system architectures. So as a quick recap, in Session 1, we discussed the economic and business drivers as to why a utility may want to implement an integrated volt-VAR control scheme. Then in Session 2, we kind of defined what the general purpose and premise of the IVVC system would be. And in Session 3, we started to look at the field apparatus that would make up the system. Now in Session 4, we're going to start to talk about the architecture, how we can get these different field devices integrated and working in a coordinated manner. So, typically we see one of 3 or 4 types of systems deployed. The first type of system is locally coordinated. And in this type of architecture, we'll see that communications is not required, and that the goal is to try to coordinate the controls locally and have all decisions made at the local control level. The second type of system is a centralized system. In this type of system, the controls are going to be made instead of locally. They're going to typically be made by one central entity. In a distributed method, it's going to be similar to a central, only there'll be many centralized, smaller centralized systems to combine into one large system. And in the hybrid, we'll see that you are running one system, for instance, of maybe a locally controlled system normally, but in the cases of a system emergency, you may switch to a different mode. So, the locally controlled architecture. So, in the locally controlled architecture, the premises are typically that we're going to try to control the voltage downstream by using a lot of switch capacitor banks. And we'll try to use line regulators only when we have very long circuits. And typically with the switch capacitor banks, instead of having 1 or 2 larger banks, we're going to have many smaller banks. So typically we're going to see in a 12 kV range maybe 600 kVAR banks, and in a 25 kV range maybe 1200 kVAR banks. And we may have anywhere from 4 to 8 or 10 capacitor banks on each circuit, depending on the length of the circuit. Then we're going to try to have the capacitor banks be the primary regulating devices on the circuits in order to try to reduce the operations on our LTCs and our regulators. And the LTCs and the regulators will be there for both backup support of the voltage and also to, after we flatten the profile, if we need to regulate the voltage down to reduce load, that would be done at the LTC level. So the architecture looks something like this, where we may have some line regulators, we may not. We're going to have a lot of smaller capacitor banks, and we're going to try to coordinate the operations between these via local settings. And the goal really is to have as few settings as possible, because we don't want to have to dispatch a lot of engineers out or technicians to commission all these controls. What we'd really like is to have a control with an auto-adaptive algorithm to where you just plug it in, it learns the system, and it automatically coordinates with other devices. And we'll talk more on that in one of the upcoming sessions. So, we're going to coordinate via the LTC, coordinating with the regulators first of all, and that'll be done via time delay. So as a general rule, the regulating device closest to the source should be the shortest time delay, and then we should add time delay for every regulating device downstream. We also would want to coordinate the regulating devices with the capacitor banks, and this is typically most easily done if the capacitor banks are voltage controlled. That way both the regulators, LTCs, and capacitors are all looking at the same sense, which would be a voltage, to make a decision. And because we want the capacitor banks to take on the operations, we would want the capacitor banks to have shorter time delays than both the regulators and the LTCs. But there's got to be a way of having the LTCs and regulators coordinate the capacitor banks in such a way that we don't get too many capacitor banks on and go too far leading. And all that will be discussed, as I said, in a future session in more detail. So the advantages of implementing a local system are, first of all, it really does not require any communications infrastructure. And if it's implemented properly, we're using voltage-controlled capacitor banks, which means that we don't need to have the line post sensors that you would need to have for a VAR control. We've got less equipment on the pole, and also less expensive control. To buy a voltage control is a little less expensive than a VAR control. And finally, it's easier to place the capacitor banks on the circuits because we can take them and place them on taps if we want to. The voltage off of a tap will be basically the same voltage as the primary circuit. But if we were to use a VAR or a current control, the current on the tap is only going to be the amount of current on that tap and not the entire amount going through the circuit at that point. And therefore, you can only place VAR controls or current controls on the main circuits. So by going with a voltage control, we're going to save a little bit of money both on the control and the line post sensors. We're going to have less equipment on the pole, and we're also going to make it easier to install the controls and the capacitors on a clean pole. We also don't have any added burden to the SCADA system. Since we have no communications, we're not adding front-end processors or additional database points to our SCADA system. If we go with a auto-adaptive control for the capacitor controls, we have very little, if any, field engineering and programming of the devices. And finally, a lot of the new controls can still capture data, long-term data logging for metering histories, possibly harmonic information, possibly sag and swell detection and capturing of waveforms, including faults. And all that operational data can typically still be stored locally, either on an SD card or within the memory of the control, and an engineer can still go out and remotely access that data when needed. The disadvantages are, because we do not have any communications, we cannot really report back any failures to the capacitor bank. So neutral current is typically not used in this type of application, because if we do detect neutral current at the local site due to a failed can or a failed switch or a blown fuse, there's no way to remotely raise your hand and report that. We also have no indication of control failures. Also, a voltage control is slightly more expensive than just an on-off type RTU that can be placed at the pole. If we do need to collect data, that data cannot be retrieved remotely. We're going to have to dispatch field personnel out to the site to get to it. And if for some reason the system is not coordinating properly and we're having excess operations on certain devices, that is not going to be seen until somebody goes out locally to upload some of the data and analyze it. So the next thing we can do with the locally coordinated is we can actually add communications. And the only reason we're adding communications is basically so that we can monitor the neutral current on the capacitor banks so that we can detect when there is a problem with the capacitor bank. We can also, if we want to, get back additional metering that can come into our SCADA system just to verify that the system's operating the way we anticipate, and also to make sure that we're not having excess operations. And if we were to start having excess operations for some reason, we would have the ability to remotely place a control and manual to stop that from happening. But the main thing to remember here is, even though we have added communications to this system, we are still running locally automatic. So the SCADA system is not making any decisions on whether a capacitor bank should be open or closed, or a regulator should raise or lower the voltage. All those decisions are still being made at the local level. With that in mind, here's what the architecture would look like for this system. So all we've done is we've added a SCADA, we've added two-way communication. Typically we don't even interface with the regulator controls, because our main concern is just getting neutral current back for the health of our capacitor controls. We could add communications to the regulator controls and get some information back from them on their health also, but in most cases it's mainly the capacitor controls we are interested in. And again, we have no control functionality here. This is metering and status only. So the advantages of this is now we can detect a bad control or a bad capacitor bank and then dispatch somebody out to fix it. We can also trip a bank off that's having problems. So if we do have neutral current, we can have some intelligence either locally or remotely that once the neutral current is detected, we can either try to retry if the neutral current may have been caused by an operation of the switch and maybe one of the phases not fully engaging. We can retry that operation several times, and if it still doesn't clear the neutral current, we can open back up or revert back to the prior state. And if the operation was not due, if the neutral current was not due to an operation, we can actually trip and lock out the bank so that we can reduce the amount of both neutral current and possible neutral voltage. It also allows us to have a better supervision of the local algorithms, just to make sure everything is coordinated correctly, we have our time delay set right, and so forth. And finally, we can get some power quality type alarms back. A lot of these controls, again, can do sag swell detection, they can report harmonic violations, and so forth. So if we have the communications, instead of having to dispatch somebody out there all the time to retrieve the data, we can start to retrieve some of that data through our communications. Disadvantages obviously are going to be cost. We've got to add cost to the control to monitor that neutral current. We've got to add a CT or a line post sensor to monitor the neutral current. And we also have to install a communications system to get that data back to the SCADA. We also have to program our SCADA. We've got to add more database points. We may have to change some of the graphics. And we're also going to have additional front-end processing capability to pull all these capacitor controls for the neutral current. And we may have to have field technicians out there now to commission the radio and the SCADA and to get the DNP mapping in each of the controls. So our next approach would be centralized with no intelligence. In this case, it's kind of the opposite of the local, where we're going to take all the intelligence and instead of removing it from the we're going to remove it from the local and move it to the central. So we have one centralized system, and each of the local controls is a dumb control, which is basically just going to do whatever's being commanded from SCADA. Typically, when we do this type of system, it typically is implemented only with the capacitor bank controls, and typically the regulators and the LTCs are left outside this algorithm, but they can be included in some cases. So what we have here is we have communications, but notice the arrows, it's one-way communications only. So what's going to happen in this type of architecture is the SCADA master will be getting data typically from the feeder relays or some other devices on a feeder level, typically watts, VARs, volts, and amps. And from that data, it will send one-way commands out to the capacitor banks when it wants a bank to open or to close. So the advantages of this system is obviously we can have a very inexpensive control out on each of the poles for our capacitors. We don't need the neutral current CT, we don't need the line post sensor CT, and we're going with one-way paging, which if you can still find it is typically very inexpensive. And we also have no settings at any of the controls. The disadvantage with this approach, first of all, is that we basically have no monitoring feedback. So since it's one-way paging, we send a command out to the control, but we really don't know whether it operated or not in the way we asked it to. Now in some systems, they may be complex enough at the SCADA centralized algorithm that it will look at the feeder VARs, send out a command, and then anticipate the feeder VARs to change by that amount, and if it doesn't, it can generate a pseudo alarm to tell you that the bank is out of service. But because we have no neutral current, it's one-way paging, we have no feedback. We can also not get any metering from the downstream devices. So the only metering is going to come from the feeder level or substation level devices. We also really don't know whether a bank is out of service, whether the control itself is, or the bank, or the communications paging device. So we have very little information on the health of any of the devices out in the system. We also don't know whether the control may have been placed in manual for some reason and left that way. And typically these centralized systems cannot work if the circuits are timed differently. So normally these centralized systems look at the load flow and the capacitors with the normal radial feeds. If you do auto restoration or sectionalizing, a lot of times the centralized system will actually have to shut down the algorithm on those particular circuits until they're restored back to their normal configuration. And if we lose communications, then we basically have a fixed bank. It's either going to be on or off depending on its last state, and this could give us difficulties on the circuit. So our next approach would be to go centralized, but now put a little bit more intelligence in the local field devices. So we're going to replace our one-way communications paging systems with two-way communications, and we're going to upgrade the intelligence in the control. Another disadvantage, by the way, on not having with the one-way paging is the control being a dumb control. Not only can it not do anything if comm is lost, but it does not supervise the algorithm. So now that we have a two-way paging or communication system, now we can convey data back to the SCADA master, and we can actually disobey SCADA commands if they're going to drive us out of preset limits. What we've done now is we replaced the one-way arrow with a two-way arrow to each of these devices, and now we've typically, or at this point, can also integrate in our regulator and our LTC controls into this algorithm. So, with two-way communications, first of all, SCADA can now get back metering, which can help fine-tune this algorithm. If we have no intelligence out here, then all the metering was obtained at this level only. But now that we're adding communications two-way to each of these devices, and we can actually transmit back metering, we can get a better profile of what's actually going on across the entire system. With the two-way communications, we can also pick up the alarming of our neutral current again. So if we have a failure in the capacitor bank or the switch, the fuses, we can get that back to SCADA, and they can take that bank out of service. Likewise, we can monitor the auto manual switches on these controls. So if a control is placed in manual, SCADA can take that particular control out of its algorithm and move on to the next control. So the advantages of this system is it's much more secure. We have intelligence now, and we can also have that intelligence fall back to a local operation if SCADA communications is lost. So if we don't have intelligence in the pole and the communications is lost, we basically have a system with very little regulation. All of our capacitor banks are going to be fixed, and the only thing that can regulate the voltage at that point are our regulators or our LTCs. With this new two-way communications, now if we lose communications, we can go back into an automatic local mode, and our capacitor banks can still be switching on either voltage or VAR, whatever you want the local control to do at that particular time. We can also supervise the SCADA system. So if we determine that we never want the voltage to be above 126, and a capacitor control that's on an open capacitor bank receives a command to close the bank, and in doing so that'll drive the voltage above 126. In the one-way paging scheme, it's going to close the bank regardless. In this scheme, it's not going to close the bank. It'll also, besides blocking controls, have the ability to force an operation. So if the voltage continues to creep up on its own and gets above 126, we can have our local control automatically open the bank back up if it were to be closed. And we can now start getting back some more of this power quality into SCADA. The disadvantages is, number one, two-way communications is going to be more expensive and more complex than one-way communications. And now we're going to be getting a lot more data back because of our two-way communications. We'll be getting more metering back. We'll be getting status points back. And therefore, our databases are going to be upgraded, and the graphics may be upgraded. So it's going to require a much more complex communications network also, because not only is it two-way, but we've got more data going back and forth, so we're going to need additional bandwidth. Our next type of architecture is the distributed architecture. This architecture is going to be very similar to the centralized, only instead of having one central location, typically at your SCADA master or your DMS, we're going to have many locations, and they will typically be substation. So what we have done is we've replaced our SCADA system up here, and we moved it down to within the substation fence. And the IVVC application is now going to run either on a substation automation system or your RTU. And that system will be the one pulling all the controls and determining when to operate which of them. So all we've done is we've taken one centralized system and broken it down into many smaller decentralized systems. Some of the advantages of that are the length of the communication circuits. If we have one centralized system, we may have capacitor controls that could be hundreds of miles away from the centralized system, and therefore it becomes very difficult to have that centralized system pull those controls directly. If we move it down to the substation level, typically now our controls may be within 3 to 5 to 10 miles of the centralized system within the substation, and therefore we can now go with differing and less expensive communication options. So we can look more at mesh radio, and we can look more at unlicensed frequencies, because the distances we're communicating are shorter distances. We also don't put any burden on the centralized SCADA master, which can be an expensive proposition. So we're not going to add anything to the centralized master. No database points, no additional front-end processing requirements, and so forth. So the final advantage is we can implement this in an easier structure, one substation at a time. So we can go into each substation, fully automate the capacitors, the regulators, get it all communicating back to the substation, test that algorithm, and get that up and running completely before we move on to the next substation. So it can be easier to deploy. Disadvantages are, first of all, now that we have multiple IVVC systems, any changes to the algorithm is going to require changes to multiple locations. So we have distributed our databases and our algorithms, and therefore we've got to be able to get out to each of those locations if we have a change. The other problem is, again, with sectionalizing. Typically, the system is set up to look at the regulators and capacitors that are typically on the radial feeders of the circuits leaving that substation. If there are normal open ties to circuits feeding other substations and the circuits get reconfigured, some of the capacitor banks on this particular substation will move to another, or vice versa, and typically these distributed systems cannot handle that, and typically they will have to be closed down when that abnormal switching occurs. Finally, we have the hybrid architecture. What the hybrid architecture basically does is it says that you're normally going to run in one mode, but you may occasionally switch to another. The most common of these would be the local mode, where typically you're going to allow the local controls to make all the decisions on their own, but either in system emergencies or maybe during peak times, your centralized system is monitoring the local, and if it thinks it can get added benefit, it may temporarily take over either part of the system or the entire system and switch it from local to centralized, and then at some time later switch it back again. The other way it can be done is going from distributed to centralized. So we could have the distributed substation automation systems running each substation, but then they can be feeding data back to the centralized SCADA. It can be running its own centralized IVVC, and again, if it sees benefit into taking over either one substation automation system from one substation or the entire system, it can then dictate commands through the substation automation systems to the end controls. So in a hybrid architecture, typically what we have is a central system that is not typically controlling but is always monitoring everything, and if it feels it can do a better job at any given time, it can overtake whatever the local monitoring function is and then seize control of the entire system. So, in summary, we have three basic architectures: local, centralized, and distributed. In the local architecture, we're going to allow the local controls to make the decisions all the time. We may have communications, we may not. If we do have communications, it's only to communicate back the health of the capacitor banks so that if we have a failure, we can dispatch maintenance crews. And also to just allow SCADA to supervise the metering at different points just to verify that the algorithm is working as intended. In a centralized approach, we are always going to have communications, and the central is going to have control. So locally, we may have very little intelligence, or we may have the same intelligence as we would in a local method. And the reason we may want that is in a centralized, if communications goes down, then you have to default back to a local method. And therefore, a lot of utilities will start implementing a local method, then add communications after the fact, goes centralized, and that way they know if the SCADA goes down, they know what to expect in the localized method because they ran that from the beginning. Finally, with the distributed method, we are just taking that centralized approach and moving it down to the substation level, mainly so that we can reduce circuit and communication costs, have a faster implementation, and reduce the overhead required to the centralized SCADA system. We also have the hybrid approach, which may be a combination of both, a local and a centralized, or a distributed and a centralized, where we're running either local or distributed normally, maybe 90-95% of the time, but centralized is still overseeing and occasionally may decide to take control of the entire system. So both centralized and distributed do require communications. Local does not, but you do get added benefit when you add communications. So we thank you at Beckwith Electric for taking the time to listen to this particular session. We hope you got benefit out of it. If you have any questions, you can submit them via our website and we will get back to you. And we hope to see you download our next session. Thank you and have a blessed day. Bye-bye.